Good afternoon everyone. I am Swarnali Hait and today I am going to present my work on barium and yttrium coated bismuth ferrite nanoparticles. My main work is based on improvement of multiferric properties of multiferric materials, which are basically materials that show two or more than two of the primary ferric orders in the same phase while controlling each other at the same time. The material that my works focus on is bismuth ferrite, mainly due to its room temperature magnetoelectric behavior for a wide range of temperature, which makes it suitable for the application purposes. However, it has some drawbacks. For example, even after being a G-type antiferromagnet, it shows weak ferromagnetism due to spin canting, but a spiral spin structure generated from Diallo-Shinskun-Urea interaction, the macroscopic magnetization gets cancelled out. And another is, due to volatile nature of bismuth, it is prone to have oxygen vacancies, which results in high leakage current. As a solution to these problems, doping with suitable metals at bismuth site or iron site of BFO is observed to work with fusion. From literature, it is observed that doping with barium 2+ ion in the position of bismuth 3+ ion of VFO results in formation of iron 4+ ion at the place of Fe3+ ion due to charge compensation. This incorporation of Fe4+ changes the magnetic spin structure from antiferromagnetic to ferrimagnetic, resulting in enhanced magnetization in barium doped BFO. On the other hand, replacing volatile bismuth ion with non-volatile yttrium ion decreases the formation of secondary phase as well as the leakage current due to reduction in oxygen vacancies. Previously, I have worked on bulk material of this composition, which shows promising results. In this work, I have investigated the effect of this composition on nanostructural form of bismuth ferrite. So, why nanoparticle? Because as I have mentioned earlier that there is a spin cycloid of a period of length 62 nanometer, which is responsible for the weak magnetoelectric properties in bismuth ferrite. This spin cycloid can be broken by only synthesizing nanostructural forms with size less than 62 nanometer. So to prepare the nanoparticles, I have followed wet chemical synthesis route. I have kept the doping concentration of barium constant at 10 atomic weight percent and changed the concentration of yttrium from 0 to 10 atomic weight percent. The XRT data of all samples confirms the absence of any secondary phase. The Rietveld refinement with acceptable R parameters implies a reduction in C by A ratio as well as the volume of the unit cell, which happens due to replacement of larger bismuth ion with smaller yttrium ion. The HRT images in corroboration with XRT data confirms the rhombohedral structure of BFO. The SAED pattern implies the polycrystalline nature of the sample. The FECM image in agreement with TEM data implies that the mean particle size of all samples are well below 62 nanometer, which is needed to break the safe spin cycloid. The P hysteresis loop indicates an increase in remnant polarization up to 5 atomic weight percent and reduction with further doping. In bismuth ferrite, the off-centering distortion along 1,1C direction of this pseudocubic cell due to stereochemically active lone pair present in bismuth ion is responsible for the ferroelectric nature. But in this sample, the off-centering distortion decreases due to replacement of larger bismuth ion with smaller yttrium ion, as was studied from Rietveld refinement. Therefore, instead of the observed increase in remnant polarization, it should have decreased. Similar behavior is observed in lanthanum doped BFO as well, where remnant polarization increases in spite of the decrease in off-centering distortion. However, for lanthanum doped BFO, the reason behind this is the large difference between electronegativity of lanthanum and bismuth. For similar reason, we here conclude that the reason for our sample as well is the change in electron densities inside the unit cell due to large differences between electronegativities of yttrium and bismuth. The electric field induced strain analysis implies a decrease in asymmetry with increasing concentration, because of which the higher substituted samples show more symmetrical nature with typical butterfly-like structure. A maximum increase by a factor of 67.7% is observed for peak-to-peak strain values of 5 atomic weight percent of sample, which is much higher than many reported values of BFO and BFO-based ceramics at low frequency. The study of leakage current indicates that the 5 atomic weight percent of sample shows minimum leakage current at zero field, while the 3 atomic weight percent of sample shows lowest leakage current at an applied field as high as 3000 volt. To explain the reason behind this, we need to know the conduction mechanism followed by these samples. The literature for BFO and similar perovskite materials discusses this following mechanisms. These are 1. Space charge limited conduction mechanism, where current arises from charges injected from the electrode, and therefore the current density here is directly proportional to the square of applied voltage. Next is ohmic conduction, where the current arises from intrinsic charges in the material and the current density is directly proportional to the applied voltage. Next is pole Frankel emission, where the current arises due to consecutive hopping of charges between defect trap centers, and logarithm of J by A is directly proportional to the square root of E. And the next one is grain boundary limited conduction, where the current or the flow of charges is limited or hindered by the grain boundaries and therefore becomes independent of applied field. To study this, I have plotted logarithm of current density with logarithm of applied field and noted down the slope values. It is observed that for 0, 3 and 10 atomic weight percent of samples, there are 3 distinct regions observed with 3 distinct slope values. All 3 samples are governed by grain boundary limited conduction. This happens when there is a large differences between resistances of grain and grain boundaries as observed from resistance values of these samples calculated by fitting real part of dielectric permittivity with frequency. However, as the field increases, the charges are now able to overcome these limitations due to grain boundaries and follows ohmic conduction. At higher applied field, that is above 400 volt, the charges interjected from the electrodes dominates the conduction. As for 5 atomic weight percent of sample, the very small difference between its resistance values are the main reason behind the high leakage current in this sample. The image hysteresis loop implies almost no change in its remnant magnetization value, which is expected as I have kept the doping concentration of barium 2 plus unchanged. There has been no more incorporation of Fe4 plus ion to change the magnetic properties. The very small increase in 5 atomic weight percent can be attributed to its increased magnetoelectric coupling nature. The dielectric study implies that 5 atomic weight percent doped sample has maximum dielectric constant value. As already mentioned before, the fitting of real part of complex permittivity with frequency is used to calculate resistance and capacitance values of grain and grain boundaries. These values are fitted with temperature following the Arrhenius equations to calculate the activation energies. The very small difference between activation energies of grain and grain boundaries for 5 atomic weight percent of sample explains its high conductivity nature, which can as well be confirmed from the study of conductivity. The activation energy of conductivity calculated is in agreement with that of the dielectric relaxation. The magnetoelectric coupling can be indirectly characterized from the magnetodielectric study. This shows that the highest change of 1.2% is obtained for 5 atomic weight percent of sample. The linear relation between magnetodielectric factor with square of magnetization further confirms the existence of magnetoelectric coupling in this sample. This concludes my work on barium and yttrium co-doped nanoparticles, where 5 atomic weight percent of sample shows promising result with enhanced magnetoelectric properties. These are my publication, and this work that I presented today is now submitted to Journal of Applied Physics on 18 June of 2021. By this, I thank my supervisor, Professor Kullan Mandal, for his constant guidance and my lab mates for their help and support. Thanks for listening.